In section 13.1, part 1, we are looking at planes and surfaces in 3 dimensions. So this is the real beginning of our multivariable journey. This is the first time that we are going to be looking at functions of several variables. Now, up until this point in our calculus careers, we have only seen functions of a single variable, our good old friend y equals f of x. And we've only seen equations of 2 variables, x and y. Now here, this is where we begin our exploration of functions of 2 independent variables. So functions of the form z is equal to f of xy. And we're also going to be looking at equations with 3 variables, x, y, and z. Now, functions and equations of this form are described as surfaces in 3 dimensions. So just like a line is the most basic equation or the most simple equation in R2, the equation of a plane is going to be the most simple surface in space. Now, we're already familiar with one plane, the xy plane. We know and love the xy plane. And we already have an intuitive understanding from the xy plane of what a plane is. A plane is a flat surface that extends infinitely in all directions. But how do we determine a surface that describes a plane? Well, a unique plane in space is determined by one of 2 methods. The first is a unique plane in space can be determined by 3 non-collinear points. So 3 non-collinear points, or 3 non-collinear ordered triplets. Now keep in mind, when we say non-collinear, we mean that these 3 ordered triplets are not on the same line. Now alternatively, a unique plane in space is determined by 1 point on the plane and a non-zero vector that's normal to the plane. So we say 1 point or 1 ordered triplet on the plane and a non-zero vector that's normal. So normal meaning orthogonal or perpendicular to the plane. Now this normal vector is important. I want you to make one little love note here that this non-zero normal vector is going to determine the orientation of our plane. So your normal vector, vector n, determines the plane's orientation. And we'll talk more about this shortly. So these are 2 methods in which we can determine a unique plane in R3. We can again use either 3 non-collinear points, or we can use 1 point that's on the plane and a non-zero vector that is normal to the plane. So now that we have 2 different ways in which we can determine the plane, we need to establish the formal definition and then use this definition to derive the general equation of a plane in space. So here we go. The general equation of a plane in space. So to begin, we need to establish the formal definition. So given some fixed point P naught, defined by the coordinates x naught, y naught, z naught, and a non-zero normal vector, vector n, the set of all ordered triplets x, y, z, for which the vector p naught p is orthogonal to vector n, is called the plane. So how can we use this definition to establish a general equation? Well, let's reread what this is saying. The set of all points, or all ordered triplets x, y, z in R3, for which p naught p, the vector p naught p, is orthogonal to vector n, is called the plane. So this is the most important part here. This is what's going to help us to define the general equation. So let's think back to our knowledge of vectors. if the vector p naught p and the vector n are orthogonal to each other, how could we define this using vector operations? The dot product. We can say that if p naught p, the vector p naught p, is normal to vector n, then their dot product is equal to 0. So if this is true, then the set of all ordered triplets p is a plane, or defines a plane in space. So we're going to use this statement here, this dot product of the two vectors, to help us establish the general equation for the plane. Now, looking at our definition, we already have the components of the normal vector. Vector n is defined by the components a, b, c, and this is, of course, such that a, b, and c are scalars. Now we have 2 points, or 2 ordered triplets. We have the point p naught, your initial point, which is x naught, y naught, z naught, and this is again such that x naught, y naught, and z naught are your scalars. And so these are real numbers. Now the other point we have defines the general variables. P is the arbitrary ordered triplet x, y, z. So we need to establish or define the coordinates, the components of our vector, p naught p, using these 2 ordered triplets. So this lets us know that the vector p naught p is defined as terminal minus initial, x minus x naught, y minus y naught, z minus z naught. So we have everything we need now. We're going to take this vector p naught p, and we're going to dot it with the normal vector to define the general equation of our plane. So here we go, giving ourselves plenty of room. By the dot product, we have the following. So again, keep in mind, we are doing the dot product of the vectors p naught p and the normal vector n. And we know because they're orthogonal to each other, their product should be 0. So plugging them in, we have x minus x naught, y minus y naught, and z minus z naught. And we're dotting this with the normal vector with the components a, b, c. So by the dot product, this becomes a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and it's equal to 0. But we need to simplify this equation here. We need to apply the distributive property and take these coefficients, these a, b, and c values, and distribute them through. This will then allow us to group up the like terms. We'll keep our variable terms, the terms with x, y, and z, on one side, and we'll bring all of our constants to the other side. So we are left here with ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. So to establish that formal definition, or the general equation, we want to bring all of these constants to the right-hand side. So this is going to leave us with ax plus by plus cz is equal to ax naught plus by naught plus cz naught. And that's the general equation of a plane in space. Now we typically rewrite this and say that therefore the general equation of a plane in R3 is defined as ax plus by plus cz is equal to d. And this is for d, of course, is equal to ax naught plus by naught plus CZ naught. Forgot my C. CZ naught. And keep in mind that this, of course, is just a scalar. This is a constant. So this is the general equation for a plane in R3. Now, as I mentioned before, we want to keep two important things in mind. And let's give ourselves a little bit more room here to define these. So we want to note that the coefficients A, B, and C in the equation of the plane describe the orientation of the plane. So we say that the coefficients A, B, and C in the equation above determine the plane's orientation. So the orientation or the direction of the plane. So the coefficients A, B, and C, the components of the normal vector in the equation of the plane, determine the orientation of the plane. And they do this by specifying a direction that's normal to the plane. So this is by specifying a direction that's normal to the plane. Now, in addition to this, I want you to note that the constant term d determines the location of the plane. So the constant term d determines the location of the plane in space. Now, what's fun about this constant term is if we hold the coefficients A, B, and C as they are, we hold them fixed, we can generate parallel planes by varying the value of D. So one final love note here before we look at examples is if we hold the coefficients fixed, we can generate parallel planes by varying D. And this is because D is describing the location of your plane. So if we vary D, we produce parallel planes. So now that we have the general equation of the plane, we're ready now to go ahead and explore some examples. So get excited.